Alright, so today I'm gonna be explaining an important paper with the title Graph Kernel Neural Networks. This paper in 2025 IEEE by Professor Michael Bronstein in Oxford University, and his colleagues. So as I said, there are many ways to capture structural information, such as anonymous random walk, any kind of random walk, but graph kernel also. Of course, all of these are equivalent. You can prove that all of these are equivalent. There are different ways of looking at the same problem. So all of them provides a very good structural information, at least local, for local, semi-local, and the global, for all the nodes in the graph. It captures the neighborhood of that structurally. So they propose graph kernels, which graph functions that compute an inner product on graphs to extend the standard convolution operator to graph domain. Of course, this was their motivation as well, because in CNN you have some filters. In convolutional neural network you have some filter. So why not using it for graphs? This idea that we have some filter, we can learn filters for graphs, and this is what this paper is about. Here they have some filters M1, M2, and M, so we have M filters, and the way they are creating is very interesting, because you just create your node embedding using this for each of the nodes V, and because you have M different filters, so Z1, Z2 till Zm, because you have M filters, and for each of them the kernel of your MI, your mask or filter, call it filter, this one should be learned. It captures this layer, and in biology it has a very good, we call it motif. It's a structural thing, and the kernel between this learned graph that should be learned and the subgraph around each node. Each node that has a k-hop subgraph, so each node V has a, so this subgraph and the kernel and the filter, we calculate this similarity using this kernel. Of course, they do expectation overall, but they also add JSON, because you don't want the filters to be very similar to each other. That's why they added this loss as well, and that's it. And of course they use importance sampling. We always use this when we want to reduce the variance, because we have so much expectation. So why not use a trick of importance sampling to have a lower variance in this statistical estimation? And that's why they write it like this. And as you see here, you have an example of model train. You see the matrix of edge observation, probabilities associated to the mask M sub I for successive epochs. And it's very good for interpretability as well, or in biology to capture the motifs as well, or anything that you want explainability, interpretability. So there are 4 significant structural masks, and they did it on, for example, MuTalk dataset. They have captured these structural masks. So because of this good capturing of structure around each node, so the global mean pooling, and so they can compare it with even diff pool. You see there is progress when you compare diff pool with this approach. You have some improvement. So it's even better than this hierarchical graph pooling of div pool, because it has more structural information. And that's it.